tons of pain. It actually makes things a lot easier, believe it or not. However, here's a little hint when it comes to polar coordinates, is whenever you have an ellipse or a circle, so things looking like this, or in 3 dimensions, we're always going to be doing circles. So we're always going to be doing polar coordinates no matter what. So that's a little hint. And you'll see that as we go along down here. Okay. So polar coordinates, we saw this way back, maybe in pre-calculus, a little bit in calculus. Polar coordinate looks like this. R squared is equal to x squared plus y squared. X is equal to r cosine theta, and y is equal to r sine theta when you convert from x to y. So therefore, when we do the double integration of polar coordinates, instead of x, y, we have r and theta. And then r usually goes from a to b, or maybe 0 sometimes because of the radius. So, and then theta usually goes from, some degree itself, usually from 0 to pi, or pi over 2 or 2 pi itself. Okay. So here's our integral. Now this is the one you got to be very careful of. We obviously convert all the function to cosine and sine. However, when we do this integral, we also multiply it by an r at the very end. That's a very subtle r. Just be careful. It makes a big difference when it comes to integration itself. Okay, so that's our conversion integration. Don't forget to multiply that single r at the very end, and we always do r d theta. So r first, then theta. Okay. Unless we really want to change the bounds, but I don't think these ones we want to change the bounds. Usually it's pretty nice to go theta last. So let's try an example of how this would work out. So I gave you the hints, right? Whenever we have x squared plus y squared plus z squared equals something, or just x plus y squared, we're always going to convert to polar coordinates no matter what. And right off the bat, you could tell we have 2 of them. So we want to find the integral of this area. Can you guys hear me? Yeah. Okay. So just making sure. Okay. So we're going to find the integral of this area of the upper half bounded by the circles x plus y squared equals 1 and x plus y squared equals 4. So just a quick sketch of what this technically looks like. So we want to find this right there. So it's just the outer parts of the circles connecting, and it's in the upper half, right? So it's just the upper half there. Okay. So when we do this conversion, we want to find the limits of r and theta. So theta is going to be the easiest one to see what converts, right? So if this goes straight to an x, the unit circle, for instance. So that makes just a big unit circle. So therefore, theta goes from 0 all the way to here, which is pi. So we know theta goes from 0 to pi. And then we do r. So r, we just plug it in respectively of our conversions. So just plug in r cosine and r sine theta into both of these. And the thing you will always be doing is remembering this special property. Cosine squared plus sine squared equals 1. And that's exactly what happens when you plug it in here. You just get r squared is equal to 1, and r squared is equal to 4. And then solving for r, we get r is between 1 and 2. Now, another little note, just for sake as well, is this a special property I'll show you guys. And this is just, you're going to be using a lot in this section, especially for your homework, is this property. What is it? Oh, yeah. Two theta? Yeah, 2 theta. And the cosine is going to be, I believe, positive. Pretty sure. Give me 1 second. Let me look at it again. Oh no, this one's positive. Yeah, this one's positive, and this one's negative. Yeah. There we go. So you're going to see me use a lot when it comes to polar coordinates, these two. Okay. And then in fact, you'll see it in a little bit with this this example. All right, so I'll put this here so you can see where I'm going to plug it in. So now I want to find this region. So this is going to be the double integral from 0 to pi of theta, and then from r to 2 of r. And I'm going to convert all of this using polar coordinates. So it'll be 3 r cosine theta plus 4 r squared sine squared theta times r, dr d theta. All right, so I'm just going to bring this r in to be 3r squared cosine theta plus 4r cubed sine squared theta, dr d theta. All right, so r is easy, right? We're integrating with respect to r, so that's a pretty straightforward one. So remember, just r cosines. It's cosine theta is just a constant. So this is going to be from r third cosine theta plus r to the fourth sine squared theta from 2 to 1. Okay. So this is one of the steps I'm probably going to skip real quick. So I'll just explain. So if I plug in 2, I get 8. Plug in 2, I get 16. And then minus 1 and 1. So I get 8 minus 1 is 7. So I get 7 cosine theta. And then 16 minus 1 is 15. So I get 15 sine squared theta. So since cosine and sine are the constant, we're just subtracting technically numbers, right? And just remember, this is cosine, this is sine, and that's why I didn't put these together. Okay. So hopefully that makes sense. Just for the sake of a little bit of time and space here. Okay, so now we'll take integral with respect to cosine. So it's a theta. So this is where I'm going to use this property I just talked about earlier. So integral of cosine is going to be positive sine. So it'd be 7 sine theta. And using this property here, it's going to be now, since this is going to be u. No, oh, sorry, this is going to be u. That's a constant. So it's going to be plus 15 theta over 2 plus 15 over 4 sine of 2 theta. Evaluate at 0 and 2 pi. Okay. So interesting, right? Because if you plug it in 2 pi into here, you get 4 pi, still 0. Plug in 0, you still get 0. So it really just depends on this part right here. And again, if you plug in 0 for any theta, it goes away. So all I'm literally plugging in is this. So that's gone. This is now going to be 30 pi over 2. That's gone. And minus, like I said, 0, right? Plug in 0 for everything goes away. So that just ends up being 15 pi over 2. That's your answer. So the hardest part is just integrating sine and cosine, as you notice, right? That's pretty much it. R is usually going to be always a nice way to integrate. And like I said, this property is going to be coming up a lot. You'll see that. Same with cosine squared. Or you could do the old-fashioned way, integration by parts, but I don't think you want to do that. It's the proof of that. Okay, let's try another one. And Believe it or not, this is actually easier. I should have swapped these examples. So find the volume of the solid bounded by the plane z equals 0 and z equals 1 minus x squared minus y squared. So notice again, here's your hint, right? We have x squared technically because I can rewrite this with a negative on the outside. So we do technically have the circle. So that means automatically polar coordinates. So again, what does this technically look like? I'm just going to give you guys a quick sketch at what it looks like. And it looks something like this. It goes to 1 and 1, 1. So it's the upper half of a sphere. Since we have z equals 0, so it's above it. So it's just this half going up. So not the whole bottom part. Okay. All right. So therefore, if I plug, again, r cosine and r sine theta into here, again, just gives me 1. Right. So the radius is just going to be from 1 here. So we know r is bounded between 0 and 1. And again, theta is from 0 to 2 pi. Now, if you're wondering why from 2 pi, so if a radius is like 1, so here's radius is 1. Pi means basically how far am I going all the way around in a flat surface. So I'm literally going all the way around the 2 pi this time. Okay. All right, so now we just plug it in to here. So we get our double integral, 0 to 2 pi, 0 to 1 of r times this in terms of r, right? And r theta. So we have 1 minus, and like I said earlier, like we did above, it's just going to be r squared. And now you notice this is much easier, right? Is everything just in terms of r. So distributed, and then take the integral with respect to r. So it'll be r squared over 2 minus r the fourth over 4. Evaluate at 0, 1. So that just gives us 1/2 minus 1/4. Which equals 2 over 4 minus 1 over 4. So 1/4. Okay, so then we take the integral of just a constant. So it's just going to be itself. And that just gives me pi over 2. There we go. Like I said, this is much easier. Let's start with this example. Okay. So these examples are nice because you could technically draw it yourself, right? It's not that bad, right? We learn how to draw this using the x-intercepts, and that's what I did here. And this is just a circle, so that kind of makes sense itself. But what if now, things get a little bit more trickier in 3 dimensions? Okay. So what I mean by that is sometimes the radius r isn't bounded by, from 0 to something. It's bounded between curves with respect to theta. Okay. It's the same process. The only difference is now our bounds with respect to theta instead of just 0 to 1 or 0 to 3 or 1 to 3, stuff like that. But just a quick little portion. So just like anything else, you just got to be careful. It's not always going to be from a region. It's going to be from like a strict value to a value itself. Yeah. So let's try a couple more examples to make this a little bit more difficult. So find the volume of the solid inside the sphere and outside the cylinder. Now, It's very hard for me to visualize what's going on here when you mean like inside the sphere and outside the cylinder. So what I did is I just drew this, put this in a three-dimensional models, and this is what it came out. Okay. So what they're asking us to do is find the region that's between or out. So on the outside of the sphere here, or sorry, outside of the cylinder within the sphere, both top and bottom. So you can think of like an apple, and you just take the center out. That's what you're looking for. Okay. So that's what I have here. So if you notice, there's a little better picture here. So it's basically this part, and then we're just going to double it, go down here, right? It's just smaller here. So as you can see now, it's kind of easier to see what the radius is going to look like. This is nice. So the radius is from 1. So again, oh, sorry, not from 1. So if you plug in r squared plus r squared and sine squared into both of these, you get a radius of from 2 to 4. So we know our radius is from 2 to 4. And then theta from 0 to pi. Now here's the problem. When we take this integral, so if we solve for z, because we have to everything in terms of z, we get z is equal to the square root of all of this. Okay. This only gives me half of the sphere. So in other words, it only gives me this part here. So therefore, to get the bottom half, we're just going to double it, right? That's the same thing. So we're just going to be integrating half of the overall portion, and just remember, we're just going to double it to get the bottom half as well. So you get the entire spherical without the little cutoff there. Okay. All right, so now we do this, and again, notice x plus y squared. So this technically becomes 16 minus r squared. Okay. So we're going to take the integral 0 to pi, and then from 2 to 4 of r times all of this. Okay. Which is good because now this is just a straight out u substitution, right? So I can plug in so that u equal 16 minus r squared. So du, making it negative 2r dr, divide it. So negative 1/2 du is equal to r dr. And that's exactly what we want there. Okay. So this is going to be the integral from, so we u to the 1/2 power. So u to the 3/2 and 2/3 times this negative 1/2 at the end, right? So if I go this back, this is going to be negative 1/2 times 2/3 of u, which is 16 minus r squared to the 3/2 power. Evaluate it at 4 and 2. Okay, so simplify this a little bit. Those cancel. And then what do we get here? So I plug in 4. 4 squared is 16, so that goes to 0. And if I plug in 2, 2 squared is 4, so 16 minus 4 is 12. So this ends up being minus 12 to that power. Oh, on the outside now. So the minuses cancel. We get exactly this. All right, now we just take the integral of theta and we call it a day. Oh, and just don't forget we're going to double it. That's it. So I'll put the 1/3 out here and the theta. So we get 1/3 12 to the 3/2 theta. Evaluate from 0 to pi, 2 pi. So we get 2 pi over 3 times 12 to the 3/2. And again, since there's only half of the region we want, we're just going to double it. So times it by 2. And just plugging this in a calculator, I get approximately 174.12. I didn't want to deal with the fractions and all that. Questions there at all? Okay, so far so good. All right, just do a couple more examples, but then finish up this section then. All right, so find the volume of the solid inside the sphere. So again, notice x squared plus y squared, and z equals 7 in the first quadrant. We'll talk about the first quadrant after we do all this stuff here. Okay, so this one's not that bad to realize. It's actually a, I don't know, like a shaker. I guess I could think about it, right? It just cuts it off at z equals 7. Okay, so first we got to find our bounds. So like everything else, we know theta is going to be from 0 to 2 pi, just going all the way around the entire portion. We'll talk about the quadrant in a little bit. Now we want to figure out what r is. So r is pretty straightforward. By looking at the picture, here's r, right? So it ranges from 0. And if you go up, 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 the question is, what's the radius when it hits the max? So when is it equal to z equals 7? And that's pretty simple. All you do is plug in 7 to here and just solve. So this is going to be 2 times x squared plus y squared. So it'd be 7 is equal to 1 plus 2 times r squared. So solving for r, right, subtract 1 and divide everything by 2, and then take the square root. So we have r is equal to the square root of 3. Again, we don't make the minus because, we're not going down, right? We're just keeping everything in a consistent basis. We can't have a radius of negative radical 3. So there we go. We got a radius. Okay. All right, so we're going to take the double integral, 0 to 2 pi, and from 0 to radical 3 of r times all of this in z formats, which I have it here. So it'll be just 1 plus 2r squared dr d theta. Okay, plugging this in, or not plug it in, but distribute it in. This is that. Okay, taking the integral. Gives us that. And 0 goes away, so just radical 3. So radical 3 squared is 3. This cuts into 1/2. And then this ends up being radical 3 to the 4th power. That's 3 times 3 is 9 over 2. And this is what 9, 10, 11, 12 over 2. Oh, beautiful. Nice 6. Okay, so now we just take the integral, 0 to 2 pi of 6 d theta. That's really nice. So this ends up being 12 pi. All right, now this is where it comes into play. It says we want it in the first octet. Now this is a trick question because octet means 8 of them. And yes, it means octate. So I'm not going to say like, yo, duh, right? But remember, when it comes to our solid is not in all the octates. So we're not going to cut into 8 parts. It's only in the first quadrants. So 1, 2, 3, 4, right? And the bottom 4 is in the lower plane. So since our solid is only in the upper plane, we're only going to cut this into the fourth of it. So we only want it in the first one right here, like for example. And it doesn't matter which one you choose, the first octet, because it's going to be the same either way. Okay, so it's like a little sliver of it. So we literally just cut it into 4. So technically, it's just going to be 3 pi. So if, for example, it was in there, we would just cut into the 8ths if it was in all 4 of the octets. But technically, it's only in our quadrants. So we just cut it into 4, a fourth of it. So that was the only trick question because it said first octet. Questions there at all? So far, so good. Yeah. So in three dimensions, it's octets, right? Just like it was in XY plane, it's 4 quadrants, 1, 2, 3, 4. So same thing here. So the quadrants are 1, 2, 3, and then 4. And then the other 4 is on the bottom when they're all negative. And since our volume is only in 4 of the octets, we just cut into 4. Yeah. So if the volume was in all 8 of the quadrants, we would cut it into 8ths. So that's always a little trick question. It says first octet. And that's usually going to be the case. Our solid is never going to be below make it negative. It's always going to be above. So whenever you select first octet, you usually just divide it by 4. Because it's only in the first 4 quadrants we care about. Yeah. That's why I said it was a little trick question. All right. So to finish up this section, let's do a hard example. And maybe hard because the integration is pretty hard. Okay. So find the volume of the solid that lies under the sphere x squared plus y squared equals z above the x plane and inside the cylinder x plus y squared equals 2x. Okay. Now, this one I definitely had to figure out what was going on. And this is what it looks like for both of them. So we have this one right here looks this one, and this one is this little cylinder part here. Okay. Now, when it says you want to be the solid lies under this value, so it's under here, above the xy plane, so above here, and inside the cylinder there. So it actually is this little right there is what we're doing. That's what we're looking for. And you can kind of see a little bit better picture here. So you can see the curvature there as a little oval. And all of this is what we're looking for. Both pictures put together. And obviously from the XY plane, so it's like this little right there. So not this, but just that. Okay. So it's a little hard to see what's going on there. Now this is the reason why it's hard is because R will not go from a number to a number. Because if I plug in R, polar coordinates in here, we get R is equal to 0. However, if I put over the same thing over here, I get R is equal to 2 cosine theta. So now R goes from 0 to 2 cosine theta, right? Because it just, goes up. The radius changes drastically depending on this nice little circle. Parabola there. Okay. Now when it comes to that, so does theta. Theta also changes as well. Okay, so this time we're not going all the way around because notice there's nothing over here. It doesn't exist on this side. So we need to figure out where does it not exist. So if we do keep this as, let's say this is 0. And if we go this way, right? So technically our solid does not start until on the other side of the axis, which is roughly like pi over 2. And our angle goes all the way around, and then it stops here, right? It doesn't exist on the other side. So this is negative pi over 2, or 3 pi over 2, if you want to do that. So our theta goes from negative pi over 2 to positive pi over 2. Now you can go from 0 to pi over 2 and just double it, just like we did last time. It's really up to you, but it means the same thing. That's exactly what we're actually going to be doing. So we're just going to be doing this. The reason why is they actually cancel each other out because the areas would go away. So we're just going to be doing this process because of this integral here. Okay, so now we take the double integral. So we're going to go from, and I'll just leave that at the very end, 0 to pi over 2. R is from 0 to 2 cosine theta. R times our region. So plug it into here, we get R squared. dr d theta. Okay. All right. So looks easy enough, right? Bring it in. This just gives you R cubed. So integral that just going to be R to the 4th over 4. Doesn't look so bad so far, right? Yep. Now 0 goes away, so we just get, let's see, what is that? So 2 squared, so 2 times 2 is 4, 2 times 2 is 8, 2 times 2 is 16. Cosine to the 4th over 4. So we're going to take the integral from 0 to pi over 2 of 4 cosine to the 4th theta, d theta. Oh boy, right? All right. Let's rewrite this a little bit. Take this out. So we get 8. Okay. So, you guys have already taken, Cal 2. So, I'm not going to bore you in how to integrate this, when it comes to it. I'm just going to give you straight what it is and just go from there. Okay. So this is the same thing as integrating. It's just integration. It's called a, what's it called? A trig substitution. You break it up into cosine squared and sine squared, make a u substitution and just plug it in. But I'm just going to give you what the answer would be. So I'm just going to rewrite this whole thing to make it easier what we're about to do. So this ends up being this for short. Actually, I'll just do the whole thing. So 8 on the outside. Integral all this using a u substitution and a trig portion gives us this. again, you can look it up. This ends up being using the property 1 plus 2 cosine 2 theta plus 2 cosine squared 2 theta. And then you use the same property I just did earlier to break it up even more. And then you just take the integral respectively of what it should be. Oh, actually, this is an 8, sorry. Yeah. But, you know, you can look it up. It's the back of the book as well. It's like cosine to the n power. Gives you a breakdown. Yeah. And then you just plug in pi over 2 everywhere. So it's up being 8 times pi over 2. Plug in pi over 2. 2's cancel. So sine of pi is 0. This is pi over 2. So it ends up being pi over 4. This ends up being 2 pi, which is 0. Minus. And I think everything is 0 as well. Yeah, plug in 0, 0, 0, 0. Yeah, that's all 0. Okay. So let's see what we get. This gives us, so if I plug in by 2, that's 4. So 3 pi over 4 times 8. So 24 pi over 4. Or 2. Oh, yeah, 6 pi. There we go.